Electromagnetic interference is disturbance that affects an electrical circuit due to either electromagnetic induction or electromagnetic radiation emitted from an external source. The disturbance may interrupt, obstruct, or otherwise degrade or limit the effective performance of the circuit. These effects can range from a simple degradation of data to a total loss of data. The source may be any object, artificial or natural, that carries rapidly changing electrical currents, such as an electrical circuit, the sun or the northern lights. EMI can be intentionally used for radio jamming, as in some forms of electronic warfare, or can occur unintentionally, as a result of spurious emissions, for example through intermodulation products, and the like. It frequently affects the reception of AM radio in urban areas. It can also affect cell phone, FM radio and television reception, although to a lesser extent. Types: narrowband EMI or Rfi interference typically emanates from intended transmissions, such as radio and TV stations or cell phones. Broadband EMI or Rfi interference is unintentional radiation from sources such as electric power transmission lines. Conducted electromagnetic interference is caused by the physical contact of the conductors as opposed to radiated EMI, which is caused by induction. Electromagnetic disturbances in the EM field of a conductor will no longer be confined to the surface of the conductor and will radiate away from it. This persists in all conductors, and mutual inductance between two radiated electromagnetic fields will result in EMI. Susceptibilities of different radio technologies. Interference tends to be more troublesome with older radio technologies such as analog amplitude modulation, which have no way of distinguishing unwanted in-band signals from the intended signal, and the omnidirectional dipole antennas used with broadcast systems. Newer radio systems incorporate several improvements that enhance the selectivity. In digital radio systems, such as Wi-Fi, error correction techniques can be used. Spread spectrum and frequency hopping techniques can be used with both analog and digital signaling to improve resistance to interference. A highly directional receiver, such as a parabolic antenna or a diversity receiver, can be used to select one signal in space to the exclusion of others. The most extreme example of digital spread spectrum signaling to date is ultra-wideband, which proposes the use of large sections of the radio spectrum at low amplitudes to transmit high-bandwidth digital data. UWB, if used exclusively, would enable very efficient use of the spectrum, but users of non-UWB technology are not yet prepared to share the spectrum with the new system because of the interference it would cause to their receivers. The regulatory implications of UWB are discussed in the ultra-wideband article. Interference to consumer devices. In the United States, the 1982 Public Law 97-259 allowed the Federal Communications Commission to regulate the susceptibility of consumer electronic equipment. Potential sources of RFI and EMI include various types of transmitters, doorbell transformers, toaster ovens, electric blankets, ultrasonic pest control devices, electric bug zappers, heating pads, and touch-controlled lamps. Multiple court computer monitors or televisions sitting too close to one another can sometimes cause a shimmy effect in each other, due to the electromagnetic nature of their picture tubes, especially when one of their degaussing coils is activated. Electromagnetic interference at 2.4 GHz can be caused by 802.11b and 802.11g wireless devices, Bluetooth devices, baby monitors and cordless telephones, video senders, and microwave ovens. Switching loads, such as electric motors, transformers, heaters, lamps, ballast, power supplies, etc., all cause electromagnetic interference, especially at currents above 2 A. The usual method used for suppressing EMI is by connecting a snubber network, a resistor in series with a capacitor, across a pair of contacts. While this may offer modest EMI reduction at very low currents, snubbers do not work at currents over 2 A with electromechanical contacts. Switched-mode power supplies can be a source of EMI, but have become less of a problem as design techniques have improved, such as integrated power factor correction. Most countries have legal requirements that mandate electromagnetic compatibility, Electronic and electrical hardware must still work correctly when subjected to certain amounts of EMI, and should not emit EMI, which could interfere with other equipment. Radio frequency signal quality has declined throughout the 21st century by roughly 1 decibel per year as the spectrum becomes increasingly crowded. This has inflicted a Red Queen's race on the mobile phone industry as companies have been forced to put up more cellular towers that then cause more interference, thereby requiring more investment by the providers and frequent upgrades of mobile phones to match. History: since the earliest days of radio communications, the negative effects of interference from both intentional and unintentional transmissions have been felt, and the need to manage the radio frequency spectrum became apparent. In 1933, a meeting of the International Electrotechnical Commission in Paris recommended the International Special Committee on Radio Interference be set up to deal with the emerging problem of EMI. CISPR subsequently produced technical publications covering measurement and test techniques and recommended emission and immunity limits. These have evolved over the decades and form the basis of much of the world's EMC regulations today. In 1979, legal limits were imposed on electromagnetic emissions from all digital equipment by the FCC in the USA in response to the increased number of digital systems that were interfering with wired and radio communications. Test methods and limits were based on CISPR publications, although similar limits were already enforced in parts of Europe. In the mid-1980s, the European Union member states adopted a number of new approach directives with the intention of standardizing technical requirements for products so that they do not become a barrier to trade within the EC. One of these was the EMC directive, and it applies to all equipment placed on the market or taken into service. Its scope covers all apparatus liable to cause electromagnetic disturbance or the performance of which is liable to be affected by such disturbance. This was the first time there was a legal requirement on immunity as well as emissions on apparatus intended for the general population. And although there may be additional costs involved for some products to give them a known level of immunity, it increases their perceived quality as they are able to coexist with apparatus in the active EM environment of modern times and with fewer problems. Many countries now have similar requirements for products to meet some level of EMC regulation. Standards: the International Special Committee for Radio Interference, or CISPR, which is a committee of the International Electrotechnical Commission, sets international standards for radiated and conducted electromagnetic interference. These are civilian standards for domestic, commercial, industrial and automotive sectors. These standards form the basis of other regional and national standards, most notably the European norms written by CENELEC. EMI and integrated circuits. Integrated circuits are often a source of EMI, but they must usually couple their energy to larger objects such as heat sinks, circuit board planes and cables to radiate significantly. On integrated circuits, important means of reducing EMI are the use of bypass or decoupling capacitors on each active device, rise time control of high-speed signals using series resistors, and VCC filtering. Shielding is usually a last resort after other techniques have failed, because of the added expense of shielding components such as conductive gaskets. The efficiency of the radiation depends on the height above the ground plane or power plane and the length of the conductor in relation to the wavelength of the signal component. At lower frequencies, such as 133 MHz, radiation is almost exclusively via I/O cables. RF noise gets onto the power planes and is coupled to the line drivers via the VCC and ground pins. The RF is then coupled to the cable through the line driver as common mode noise. Since the noise is common mode, shielding has very little effect, even with differential pairs. The RF energy is capacitively coupled from the signal pair to the shield, and the shield itself does the radiating. One cure for this is to use a braid breaker or choke to reduce the common mode signal. At higher frequencies, usually above 500 MHz, traces get electrically longer and higher above the plane. Two techniques are used at these frequencies: wave shaping with series resistors and embedding the traces between the two planes. If all these measures still leave too much EMI, shielding such as RF gaskets and copper tape can be used. Most digital equipment is designed with metal, or conductive coated plastic, cases. RF immunity in testing. Any unshielded semiconductor will tend to act as a detector for those radio signals commonly found in the domestic environment. Such a detector can demodulate the high-frequency cell phone carrier and produce low-frequency demodulated signals. This demodulation manifests itself as unwanted audible buzz in audio appliances such as microphone amplifier, speaker amplifier, car radio, telephones etc. Adding onboard EMI filters or special layout techniques can help in bypassing EMI or improving RF immunity. Some ICs are designed to have integrated RF filters or a special design that helps reduce any demodulation of high-frequency carrier. Designers often need to carry out special tests for RF immunity of parts to be used in a system. These tests are often done in an anechoic chamber with a controlled RF environment where the test vectors produce a RF field similar to that produced in an actual environment. RFI in radio astronomy. Interference in radio astronomy, where it is commonly referred to as radio frequency interference, is any source of transmission that is within the observed frequency band other than the celestial sources themselves. Because transmitters on and around the Earth can be many times stronger than the astronomical signal of interest, RFI is a major concern for performing radio astronomy. Natural sources of interference, such as lightning and the sun, are also often referred to as RFI. Some of the frequency bands that are very important for radio astronomy, such as the 21 cm HI line at 1420 MHz, are protected by regulation due to spectrum management. However, modern radio astronomical observatories such as VLA, LOFAR and ALMA have a very large bandwidth over which they can observe. Because of the limited spectral space at radio frequencies, these frequency bands cannot be completely allocated to radio astronomy. Therefore, observatories need to deal with RFI in their observations. Techniques to deal with RFI range from filters in hardware to advanced algorithms in software. One way to deal with strong transmitters is to filter out the frequency of the source completely. This is for example the case for the LOFAR observatory, which filters out the FM radio stations between 90-110 MHz. It is important to remove such strong sources of interference as soon as possible, because they might saturate the highly sensitive receivers, which means that the received signal is stronger than the receiver can handle. However, filtering out a frequency band implies that these frequencies can never be observed with the instrument. A common technique to deal with RFI within the observed frequency bandwidth is to employ Rfi detection in software. Such software can find samples in time, frequency or time-frequent space that are contaminated by an interfering source. These samples are subsequently ignored in further analysis of the observed data. This process is often referred to as data flagging. Because most transmitters have a small bandwidth and are not continuously present radio devices, most of the data remains available for the astronomical analysis. However, data flagging cannot solve issues with continuous broadband transmitters, such as windmills, digital video or digital audio transmitters. See also, electromagnetic radiation, Faraday cage, radio receiver, signal noise, twisted pair, interference, references. External links, ARRL, RFI, Interference Handbook, EMC Design Fundamentals, Clemson's EMC page, EMC Tutorials.